put it into the modeling language and try to solve it. And they could have all these data sets for different products, and when they were testing it out, they could have 50 products they could try. And just put them in a loop and try one after another and see what they got. And it probably took a fair amount of experimentation to get the form of this correct. And this is the sort of thing where you need to be able to try a lot of things quickly in order to get to a point where you have something to show fast enough before the management loses interest. And this is really the hard part of the model. And you see that it relates Z to V, Y and V, and then Y to X, and so it really ties all this together. Okay? And you see I'm not trying to explain exactly what this is, but it uses various piecewise linear demand functions and so forth, and is really quite complicated. Okay? And it's typical, these models, they have an easy part, and then they have a complicated part. So, let's see, I have just about enough time left to show the other example, which is a production distribution model. And that was developed by Norske Skog, which is a Norwegian paper manufacturer, which over time came to own paper plants throughout the world. And so they started out with a group in Australia and New Zealand who built a model for production and distribution of paper. And when that was successful, they later built a model that covered Europe, and this is a fairly large model. It had about 500,000 variables. I mean, by current day standards, it's not so terribly large. But the challenge was to develop this, as we'll see. The challenge was not just to be able to solve it, although that was really important that they could solve this quickly. We'll also see that. Okay? And the reason was that the third model they developed was optimization worldwide. And it came at a time when the demand for paper was dropping, and they had to decide which plants to close. And in order to decide which plants to close, they had to ask themselves, what is the optimal choice of plants and paper-making machines to close in order to maximize their expected profits going ahead to the future. Okay? And this required running a number of different scenarios, so they couldn't just run this once. They had to try different scenarios involving different assumptions about how the paper industry demand might be in the future, and numerous sensitivity analyses where they varied different numbers and reran it again. Okay? So it was important that nowadays you can solve these problems in seconds because they had to solve a lot of them. Okay? And the key role of AMPL here was that actually once they had done this global optimization model, which we'll see was quite complicated, was able to be developed in only a few weeks and could be modified to analyze alternatives as the company debated which plants to close. And to the extent that actually at meetings where they discussed the closure decision, they would interactively run this model with different decisions that people brought up. They would say, what if we did this? And they would go back and run it again. And the fact that it's so easy to make changes to this was essential, because they had to reliably keep changing and rerunning this model over a decision period, okay, without having to say, well, if you want that change, we'll have to go back to our implementation team and we'll need a couple weeks to rewrite and debug all the code. Okay? And this is where really the modeling language comes into its own, for this sort of quick decision. And what they were trying to do was to essentially look at the profitability of the different plants and see what they closed. And the problem is that previously they would have looked at a graph like this and said, well, we'll just close the ones at the bottom. They're the least profitable. But it turned out that was very misleading for various reasons, that you had to look at the plants all as a whole, and that's why they needed the global model. Now, how complicated is a global model? Well, it has all these sets. So they just describe their sets in terms of the number. Mills, machines at the mills, paper, okay, total number of paper machines, products, raw material sources, raw materials, customers, and recipes for making paper. There's different kinds of paper they can make. Okay? They had to take all these into account. Okay? And so then the parameters, I divide them into two kinds. They're the capital parameters that have to do with deciding what to close. things like the fixed costs of running different things, fixed costs to be saved, time that you have to shut down a machine before you save any fixed costs, and the amount you might save from a permanent closure. Then on top of that, there's all the operational data, the operating parameters, which have to do with freight costs for shipping the product. There's the logistics, and also the capacity for making things, various kinds of costs incurred, raw materials needed. Okay, so there's the cost of getting the raw materials and the amounts needed, the amounts of supply that are available, and then for each product and each customer, the demand and the sales price. So a huge amount of data has to be brought into this. Okay. And what does that mean then? Oops. Well, in addition to all that, there are now the variables that we have to define. What are the decisions? Instead of just having two types of decision variable, in this problem it was much more complicated. These Greek letters stand for 0, 1 variables. Okay? They represent whether they close a certain paper mill, whether they shut down a machine at a mill that's not closing down, okay? Whether they can accrue some savings. Okay? So these have to do with the capital decisions. And then there are all the variables that have to do with the operation. Okay? And that's how much each product to make sure on each machine of each paper type, and how much to deliver to each customer. Okay, this is very important. If you shut one down, you have to deliver paper to the customers from a different one. Okay? That might cost you more to ship, but that plant might be more efficient. So you have to build all this together. Okay? Tons of raw materials used by the machine, and one more 0, 1 variable that determines which recipes you put on which machines. And now, in terms of that, this is the objective function. It puts together income from sales, and then various kinds of costs, plus the capital costs and savings due to shutdowns. So you save something from shutdowns in the long run, but in the short run they cost you something. And they had to put together all these into one large linear objective, which you see is quite complicated. Okay? But this could be written in AMPL just like you see it. This would be called SUM, sum, and so forth. These would have names, but this exact thing appeared in the AMPL model. Okay? And the same goes for the constraints. Okay? They had all these operational constraints. These are things like capacity constraints, production, shipment constraints, and raw material use constraints. Okay? So these are the kind of linear constraints you would expect in a production distribution model. But then, due to the shutdown decisions, there's another whole kind of constraint that appears in these, and that looks like this. So I just wrote them all here without trying to actually put a description of every one of them. Okay? But there's 6 different classes of constraints that all of them involve these Greek letters. Okay? So all of these involve the 0, 1 decisions and relate one kind of 0, 1 decision to another. Okay? And they say things like, well, if you shut down a plant, then you can't ship anything from that plant. Okay? And that's what this is saying, essentially. And that kind of thing. So they actually had 11 kinds of constraints in this one model. Okay? And when they were making this decision, changes came up frequently. They were asked to consider, well, what if we did this and that, and they had to make modifications to this complex thing. And because the thing they were giving to the computer looked very much like the math that I wrote there, they were able to make these changes quickly and reliably, as they were confident that when they made a change, it was the change they intended. Because they could read the AMPL and it looked like that. Had all the same components in it. So that's the second example. And you can see why both of these qualified as finalists for this prize. They were really quite ambitious uses of operations research techniques to solve very practical problems. So I'll just say that AMPL alone is used also in many government things, a lot in finance, so a lot of financial agencies, and also being a U.S. company, most of our other government users are currently in the United States, although I expect this will change gradually. And so things as different as the Bureau of the Census and the Army Corps of Engineers have applications that use the AMPL language, as well as various national laboratories. Now, another big area of use is academic research and teaching. There are over 250 university installations of this language, and nearly 1,000 citations of it in various kinds of scientific papers throughout engineering, science, economics, management. So just about any area of engineering, for example, people have found some use for optimization. And often you go outside the people who are operations research experts, and they're not experts on solving optimization problems. What they want is a system that lets them formulate their problem and try solving it. And this is what it gives them. And then for teaching, the nice thing about a language like this is that, of course, it's easier to present to the students as well. And it's something they can pick up relatively fast and try out and learn something in the duration of a course. So it's, of course, used in linear and nonlinear optimization courses, and operations research courses, and various kinds of specialized courses for things like supply chain modeling and electric power system planning and these other things. Now this list, where did I get this list? We started a new program this fall where we offered to give people this software for courses free for the length of the course. And this is basically taken from the 30 to 35 courses that used it this fall, the first time we had this. So these aren't just courses that have used it sometime, they're courses that used it this past fall. Okay? And this free thing, basically, we tried to set it up so that someone who's teaching a course and has many other things to think about besides somebody's software could get this very quickly and make it available to all the students quickly. And then at the end of the course, it would just time out. So it would stop working after the course is over. And since it's going to stop working after the course is over, we removed any limitations on the size of the problem. So it basically gave the students ample and top quality solvers to use for the duration of the course. So they have just as much as any company would have. Okay? It's just that the version they have, at the end of the term, 2 weeks later, it stops working. Okay? There's a timeout inside the code, and it won't work any longer. And that's the only difference there. Okay? And so this is available now for the spring courses as well. We hope to increase the number of people using it this way. And so encourage more courses that involve some kind of optimization to actually get the students using something that will let them build complex models. And as far as future developments, of course, you can make anything that will make the language more natural is desirable. The whole idea is to make it as much like you think as possible. We've gone a certain way toward that goal, but we could go further. And the other work is a lot of it is interface development. That one weakness of the system might be that it doesn't interface so easily with other things in the world. Optimization is seldom the entire application that somebody wants to do. There are other things involved, and so there are various interface issues that we want to get involved in. And also maybe making it available over the internet rather than requiring installations on individual computers. So there are some references, and that brings me to the end of the talk. I thank you for your attention. Okay.
Okay, thank you very much for introducing basic structure of AMPL and good case studies. And now we would like to close morning session, but finally, please give big hands for two distinguished presenters again. Okay, afternoon session will start 2 p.m. and please enjoy lunch and return here by 2 o'clock.
And we also have a cafeteria downstairs. And also, if you would like to go outside, you will have a lunch map inside the proceedings. And we also have some copies at the registration desk, so you can take, if you want, some copies.